For robotics engineers, one challenge stands out: the black box of failure. You train a state-of-the-art policy, deploy it, and suddenly the robot fails. Maybe it jittered uncontrollably, or the server just couldn't keep up with the command. Staring at raw logs won't answer these questions. Today, we are going to show you how to turn this black box into a crystal clear insight using dFL. dFL provides the tools to visualize, label, and deploy insights in minutes, enabling a rapid loop from data collection to policy refinement. The data we're using here is the SO-100 sorting dataset pulled directly from the LeRobot Hugging Face repository. It includes high-dimensional state data like commanded actions, observed server positions, and end-effective states. As per the requirements for integration with dFL, we have the data provider script, and in addition, we make use of two supporting scripts to download the dataset from Hugging Face and process the raw data into dFL's readable format. The processed data has records representing a single episode, making it easy to compare successful runs against failed ones. Let's begin our analysis on dFL. The default grapher gives us an immediate look at the mechanical fidelity. First, we plot the commanded action versus the real observation for the elbow joint. The dual tracer shows exactly how closely the server is following the policy. See this gap? This isn't a code bug. This represents a physical lag where the policy is moving faster than the hardware can handle. This gives us a crucial baseline for mechanical stability. We can now perform manual labeling of the certain so-called misalignment through dFL. So this visual analysis gives us a fantastic intuition for a single episode. But the real goal is to turn these discoveries into an automated labeling system. We need a way to flag this misalignment failures automatically across thousands of training episodes without an engineer watching every second of the data. This is exactly what dFL's auto-labeling is built to solve. The misalignment detector is a custom auto-labeler that was deployed via the Robotics data provider. It was generated using an LLM prompt similar to that seen in the manufacturing demo. This isn't just a simple threshold check. It calculates the rolling difference between your command and the reality over a sustained window. For enthusiasts building custom arms or tuning PID controllers, this is a game changer. It instantly tells you which joints are too heavy, which motors are stalling, or where your PID gains are too low. As I click on the auto-label record, you can see the time series graph immediately highlights every instance wherever the sustained error exceeds our threshold. It instantly filters out the episodes where misalignment lies. We can run the same in bulk across the entire dataset using our bulk auto-labeling feature to find all the failures in all the episodes. The proposed labels are documented in the current proposed labels table. We can now toggle across multiple episodes to visually see the detected misaligned region given by the autolabeler. From here, the workflow is simple. We first confirm all the autolabels. And from our current labels table, we can now download all the labels from the records. You can now export the curated golden dataset for training or use the flagged episodes to refine your smoothing algorithms. And this is the end-to-end workflow from raw LeRobot logs to dFL-assisted automated insight and a clean high-performance policy. Thank you for your attention.